The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams, and joining me today, the special guest, Dr. Slava Turyshev. Doctor, how you doing?
Very nice. Thank you very much for inviting me to your show, Math. So it's excellent to be here. So thank you.
Yeah, and shortly before we started getting into things, I was noticing Dr. Turshev's background, which is French Polynesia, and he told me a very interesting tidbit there. Would you like to repeat what you said for the listeners?
Look, when Polynesians, they actually gave us a very good example how humanity may travel among the stars. Because back then, when they were exploring Polynesia, sailboats would travel from one island to another, and navigation was done using stars. So they would train their kids to be sailors in the future. They would train their kids how to sail among the stars. At night, they would navigate from one star to another. And remember, at that time, they didn't have written language. They had only spoken language, and all the culture is based on songs. So the songs would contain information, navigational charts, if you may. So you travel from one star, travel for several days at night and day, and then at some point you reach that star, you turn left, and then when you start seeing grass on the water or birds flying nearby, that means you are nearby the island. Why it is interesting is that at some point humanity will leave the cradle that we call solar system and will travel to among the stars.
Now, you are part of the Structure of the Universe Research Group at NASA JPL. That's correct?
That's correct.
Yes. And your work entails examining the first stars and galaxies in the universe, the mysteries of dark matter, dark energy, cosmic evolution. But right now, the thing you are probably best known for, and as I understand it, your favorite thing ever, is the study of solar gravitational lenses. So, can you give us a quick rundown about what that is and why the study of gravitational lenses and anomalies is so important right now?
Excellent. Let me answer this question by giving you an example. For example, if I want to image a nearby exoplanet, and I take our own Earth as an example, and I move that object, that planet, to 100 light years away from us. So it's still our neighborhood, it's still our backyard. But to image that object with just one pixel using conventional telescopes, I would need to have access to a telescope with the diameter of roughly 90 kilometers. 90. So that's almost the altitude when people fly to suborbital flights, reaching the space, it's about 105 kilometers. So that's the diameter of a telescope we need to have to image an exoplanet with just one pixel. But as we all familiar today, so our cell phones carry sensors which allow us to make pictures of, nature, friends, loved ones with the high resolution images. So we became accustomed to image everything with many, many pixels. So it's not enough having just one pixel. We need to have many pixels. But if you want to image that Earth, exa-Earth, with roughly 600 by 600 pixels, you need to multiply 90 kilometers by the number of desirable pixels. So what I'm saying is that classical technologies, classical instruments will not allow us to image the exoplanet directly. So whatever we have flown to date and whatever we will fly in the next, I would say, 30 years, will allow us to get exoplanets, information about exoplanets sort of indirectly. We will be able to see big blobs of light, but nothing of high resolution. But nature came to as a rescue. Nature came to help us, and the nature is telling us when the light travels by a massive body, the trajectory of light is no longer a straight line. Essentially, that trajectory is bent towards the body. So, according to general theory of relativity, Einstein's general theory of relativity, when we use that theory, we can actually study the light propagation around massive bodies, such as the sun. In the solar system, because the sun is the most massive body, so we will benefit from that, from its mass, and we will use the sun as a lens. So essentially, when the two light rays travel in opposite sides of the sun, they will converge at a large distance from the sun. So nominally, the focal region of the solar gravitational lens starts at about 550 astronomical units away. And so if we are able to fly a telescope with just 1 meter diameter, a 1 meter telescope can travel in the focal region of the solar gravitational lens, and it can image that exoplanet with about 7 months. So imagine that if you fly just single telescope, it's a 7 month. If you fly several of those telescopes, inexpensive telescopes to that region, we will be able to make images of that exoplanet pretty much in real time. And then what it means is that not only can we make images, but also spectroscopy. And spectroscopy is very important because with spectroscopy, we can actually confirm the presence of gases that exist in the presence of life. We're talking about oxygen, nitrogen, methane. And so flying those telescopes with technologies that are already available, we will greatly benefit from the presence of the solar gravitational lens. And the solar gravitational lens we just discussed, it's basically we use any mass, and in this case, it's the solar mass, which is the largest accessible mass for us. And when light travels around that mass, basically that mass acts as a lens. And so nature gave us that present. So the sun is the biggest lens we have, and the technology that we have already will allow us to fly there in the next, I would say, 15 years. We are now developing technologies that will allow us to do just that, to image exoplanet in our lifetime.
And in fact, you wrote a proposal paper for such a mission, a telescope that could fly to the solar gravitational lens's focal point back in 2022 with Victor Toth. And in fact, I just found the video shortly before we started talking where you were speaking to my boss and colleague, Fraser King, about this. Yeah. Now, gravitational lensing, this has been used by astronomers for decades to get a clearer view of objects that are much farther and would otherwise be much harder to study. And in fact, your proposal paper, I believe you said, in fact, we could view exoplanets using this lens with the resolution and clarity as, say, what it's like to look up at the moon in the night sky.
It's even better. With the resolution that we will have, we will be able to see the moon with many, many pixels. And so with resolution that solar gravitational lens allows us, we can actually see the thickness of a human hair on the moon. Not just the hair, but the thickness of the human hair. But because we will be observing that object with a large telescope, we will be averaging that resolution. We'll not get to that resolution, but we at least will be able to image that object, which is otherwise inaccessible to us, with about 6 by 600 pixels. And we have been funded to do this work by NASA Innovative Advanced Concept Institute. So NIAC had funded 3 proposals from us: phase 1, phase 2, phase 3. And since 2017 until 2022, a large group of people worked not only on the science of the solar gravitational lens, not only to study its optical properties, but also on the mission design. So design a mission that would utilize a constellation of small sats, inexpensive vehicles that will be propelled by solar radiation pressure to reach very large velocity. And once they travel all the way to the solar gravitational lens focal region, we will be able to use optical communication to communicate. We will have radioisotope thermal generators to power their electronics and to be able to collect the data, pre-process the data, send it back to the ground. And on the ground, we'll be able to, once the data is received on the ground, we will be able to collect, interpret the data, and recover the image pretty much in real time. And so that is something that we have studied, and we confirm that indeed this mission is feasible with technologies that either already exist or in the development. In fact, we come up with this set of technology demonstration missions, essentially to demonstrate the capabilities that solar sails will allow us to achieve in the next few years. So our first mission, we are aiming to fly around the sun in about 24 months from now, and that mission will velocity is twice the Voyager speed. It will be a record-making mission that essentially speed record will be beaten by a factor of 2, and then there will be a series of those missions that will be designed not only to reach high velocity, but also to improve the technology and essentially ultimately reaching the velocity of roughly 7 times the Voyager in about 10 years from now. So the idea is that with this type of technology, we can not only ultimately, I'm interested in this technology to reach the focal region of the solar gravitational lens, but with this technology, we can explore solar system much faster and with inexpensively, so sort of very cost effectively. Because with these missions, with this type of technology, we can actually reach orbits that otherwise are inaccessible or very, very expensive. For example, polar orbit around the sun within the solar polar imager mission. We can, with solar radiation pressure and the solar sails, we can actually change the inclination, orbital inclination of the sailcraft pretty much 3 degrees every 27 days. And if we do that within a year, our orbit is exactly polar. And polar orbit around the sun will allow us to image the sun from all regions. And what is exciting about that, if you remember when Cassini spacecraft was flying around Saturn, polar regions of Saturn have shown us very exciting images when you see hexagonal structure on north and south pole of Saturn. Similar structure exists on Jupiter as well. And so heliophysicists expect that Sun will have that similar structure in the polar regions. Nobody have seen it, those structures on south and north poles of the Sun. So our mission will be able to image the Sun, but also monitor its solar activity. That is an amazing mission, very inexpensive, but it can be done soon. Also, with this type of technology, we can also look at Earth as an exoplanet. Because look, most of the technologies, most of the exoplanets that we discovered today, we use something that we call transit method. This is when exoplanet transits the face of its host star. And we, using this technique, we were able to discover many exoplanets. And now we also are able to really to detect atmospheres and study atmospheres on those exoplanets. But what does it take to confirm life in those atmospheres? For that, we can use the same technology and essentially observe how Earth will transit the sun. And so for that, we can see how Earth transit in the sun. We can actually look at spectra that will be blocked by Earth, and we can look at the results of this investigation to see if we confirm life on our planet. That will be interesting. So to inform technology development so that we'll actually be able to observe not only Earth transiting the sun, but also Venus and Mercury. And so these 3 planets show very different behavior. And this is a good sample for us to utilize and confirm that we can actually detect life and then deploy this technology on the transiting missions to look for life around on exoplanets and nearby stars. But to do this, you need to have either access to very large chemical propulsion or using solar sails again. With solar sails, you fly about 40 lunar distances away, and you are in a very good position to look at the Earth transit in the sun, and so on. So there are many other missions. For example, solar sailing mission can fly to Enceladus and get through the plumes of Enceladus and essentially sample the plumes in confirming if there is organic exist in the plumes. So what I'm saying, there is a whole set of missions that we can actually study inexpensively and within a very short time frame. The challenge now in planetary community is that, for example, if you take a fresh PhD student and she would get her PhD in a reputable university, she will then get into a very interesting, very solid, very good laboratory, very good institute that involves space studies. They will write a proposal to NASA or other agency. On the first time, they will fail. On the second time, they will improve the proposal. By the third time, they will be successful and they will start building their mission. So by the age she is 50, she will see her instrument on the launch pad. I'm talking about very long time it takes for the community to develop any missions that explore solar system. So that should not be the case. With solar sailing, we can actually, inexpensive drones can fly everywhere in the solar system much faster. And we can use them like drones to explore, to do some science, to investigations before flagship missions will get there. It is something changing paradigm of exploration in the solar system. Essentially, it allows sort of democratization of access to deep solar system, so that not only senior researchers ultimately will get their way to do things, but young scientists will be able to do this as well. So that's what we're trying to do with solar sails. But for me, ultimate objective is of course to get to the focal region of the solar gravitational lens.
Yes. Well, in fact, yeah, this increasing access, the democratization of access, the name of the game there is, and this is where commercial space comes in. It's where space agencies work and cut costs and make things reusable. And that ought to just open things. Well, and we're seeing that, aren't we? But it would be very wonderful to see that all the way to the outer solar system. Well, so yeah, you raised a point here, which I wanted to ask. Currently, if we are talking about James Webb, Hubble, the most advanced telescopes we have, and their exoplanet research, in terms of looking for emission spectra, I mean, we're really just scratching the surface there, right? I know that it's been talked about endlessly for years how we could do that, if and when, and Webb has now proven we can by getting transit emission spectra. But compared to what a solar gravitational lens could show us, right? Right now we're looking at dots, points of light around a star, and we're inferring based on the chemical signatures whether or not they could have life. But bottom line here, with a solar gravitational lens, we could see that life at work, right?
Exactly. With solar gravitational lens, we have the chance before we will travel to those exoplanets, way before, we can, within our lifetime, we will be able to do the following. We will be able to have high resolution images of those objects. We're talking about if objects are nearby, let's say Alpha Centauri, maybe a little bit further, we're talking about megapixel images of those objects. Megapixel, it's a lot. So we can see continental lines, weather patterns, topography, structures on those exoplanets. But that's not enough, because people will say, who cares about the picture? Picture is wonderful and it's worth 1,000 words, I understand. But what does it do for confirming life? And here spectroscopy comes to help, because now we can have spectroscopic studies from, let's say, from 1 to 10 micron band, where all the important life signatures exist: oxygen, nitrogen, methane, all the other composites. And we can now not only detect spatially resolved, not only can do spatially resolved spectroscopy, meaning we can identify a particular emission of methane emission from a particular spot on the planet. So if there is a swamp, we know that that swamp emits a lot of methane. Or if they have oil leakage like we do, we'll definitely have that oil leakage detected. And if they use the same carbon fuel technology as stupidly as our civilization does, we will see that as well. But then if we don't see that, if we see sort of different technology development, that also will inform us on how to treat our planet. So there is a lot of benefits of correlating spectroscopy with optical imaging. So by that, we will identify the emission, we'll identify the cities if they exist on those planets. And I'm not using those words lightly, because I'm still trying to avoid using words aliens and the technology. We don't have any confirmation on that. But that opens up the science fiction cover from this research, because suddenly now with the solar gravitational lens, we have the technology to start asking those questions. What if we are not alone? What does it mean for us, for the human beings? Look, only 70,000 years ago, human beings were sort of unimpressive animals that were roaming in the one corner of Africa. 70,000 years later, you and I are having this conversation. Through this time of evolution, we evolved from tribal structures, we built social structures on the planet, started traveling, steam engines, airplanes, boats, spacecraft. Now we're thinking about what would be the next step to explore our galactic neighborhood. And that's what humans can and should do. And with this understanding, we are now opening our eyes to the skies and asking this question: what if somebody else is out there? How do we actually make a contact? Or what do we see first? So those questions that were answered only in science fiction. Now we seem to have technology that will allow us to reach those questions and start answering them.
Well, that would be absolutely wonderful. And in fact, too, a word I've been wanting to throw out here, technosignatures, right? That is the difference between astrobiology in general and the search for extraterrestrial intelligence. So, yes, we could see city lights on another planet, assuming that such technology was used, but also built up structures, infrastructure. Yeah, it's very, very exciting. And what you said earlier, people may say, what good's a picture? If I were to summarize what I'm hearing, it would be that, well, the picture tells us where we should explore. Because what good is a mission that costs us so many billions of dollars, possibly $1 trillion, if it arrives and says nothing but balls of rock here? It's like, well, that's good to confirm it. That the fact that we sent the probe alone is great, but God, we're really hoping to find something. What do we do now? Go to the next one? That was, yeah. It's like that project's not going to be repeated, I don't think. Not for that price.
And I think, look what is happening. We actually amazing missions that are now in space, and those that we are building, like James Webb, like Hubble used to be, or still is. There are many other missions. Roman will be still soon in space. There will be Habitable World Observatory. Those missions will inform our target selection criteria. So they will provide us with a list of targets of high value where we can go, being guided by those missions. So we definitely need those missions before we'll deploy a fleet of small spacecraft to the focal region of the solar gravitational lens. So those missions, by now, as you're aware, we have a list of roughly 10,000 exoplanets discovered. Majority of them are hot Jupiters. So exactly on those planets that we don't expect to see life. But little by little, we're actually getting the list of terrestrial planets populated. And soon we will have a good list of planetary candidates, those that resemble our own planet, G-type star with the solid surface with atmosphere. And then we will realize that this planet definitely exhibits a lot of interesting behavior, but we will not be able to see life there because our instruments that are now in space, or those on the ground, the largest telescope on the ground is 39 meters in diameter, built in Chile in the European Large Telescope. So this telescope will be able to see only blobs of light, will not be able to resolve and to have a very good resolution images even with 1 pixel. Will be just blobs of light reflected off the surfaces of exoplanets and some spectroscopy. This will be wonderful, but to improve on that, we need to either travel there or actually do imaging before we travel in there with the solar gravitational lens. And in my understanding, I think humanity will be able to travel to those worlds within about maybe 300 to 400 years from now. So, but I think with the solar gravitational lens, we will start looking at those planets within about 30 years from today, 35 years from today. And see, the focal region of the solar gravitational lens is not just single point. It's a semi-infinite focal line. So we don't need to stop at the focal point. We actually launch a spacecraft and will continue coasting essentially along the predetermined line, and will be still looking back at the sun using the instrument that we call coronagraph to block the solar light, and then imaging that Einstein ring that will be formed around the sun. And that Einstein ring will have all the information about the exoplanet. And that's something is very interesting. Look how it works. How solar gravity lens or any gravitational lens is a good projector. Imagine yourself sitting in a movie theater. Behind you, there is a projector. In front of you, a large movie screen. So what projector does, it projects a compressed image on the screen. And so on the screen in front of you, when the light reflects off that screen, your eyes, your retina gets the image. But now imagine if there is no screen. Projector still works and the light still goes somewhere, but nothing to reflect from. So you don't see the image. You go up on stage to recover the image. You look back at the projector. You don't see the whole image that projector projects. You see only flickering light from projector. What you need to do, you need to move your eyes from point to point in a planar arrangement, X and Y direction. Once you go from point to point, you collect all the information and you process in your brain the image that projector actually projected. That's what we will be doing. So we know how to do the imaging with the solar gravitational lens. We know how to process the image. We know how to remove the imperfection of the solar gravitational lens from those images. And we have the understanding how we can actually remove cloud cover from the exoplanet, how to account for diurnal rotation, for orbital motion. And we have a very good understanding how mission that will be able to image the exoplanets can be built. And so that's something is very unique understanding these days. And so with this, we are building the community, we're essentially building something called a public-private partnership to start developing the mission, raise the funding, and essentially start making first steps and flying those technology demonstration missions to bring the maturity of the solar sailing technology to the level that is needed to go to the solar gravitational lens. So for us to launch it mid next decade.
Well, that's a very encouraging timeline there. Now, this is a purely speculation, but I was sort of thinking about it as you were saying this. So solar sails, they are cost effective. We know they work. And of course, the idea of directed energy propulsion and light sails, right? Breakthrough Starshot, Project Lyra, and a handful of ideas. Now, if I were Yuri Milner, and I came to you and your colleagues and I said, we really like your idea, and we think that would be a good pathfinder for studying neighboring star systems, and then we know exactly where we should send spacecraft. Would you be interested in joining us? Because we are hoping to build that laser array, and then we can send your telescope right out to the focal point of the sun quicker. Well, I'm not sure how much quicker, but I imagine it would shave many years off of its arrival. If is that a feasible idea?
If you want to send a very tiny spacecraft, like 4 grams, 4 grams spacecraft, actually 1 gram spacecraft, and to move it with a fraction of the speed of light. So for breakthrough Starshot is talking about 20% of speed of light, moving with that speed. So then you can actually envision a tiny spacecraft, which is 1 gram. You printed the whole spacecraft. It's 3D printed spacecraft, very lightweight with all the systems. You put it on a 4 by 4 meter sail, and then you can actually propel that spacecraft with lasers. And laser for that you need to coherently combine light from about 1,000 by 1,000 units. It's an array of like million lasers, 1 kilowatt lasers, to put about a gigawatt energy on the sail. Then you are able, if you're able to control that sail, you can accelerate it to very large velocity, and potentially you can travel to Alpha Centauri system within about 20 years. That's something can be done, I guess, with technology. And I think this is what Breakthrough Starshot is trying to achieve, developing technologies to travel there. But we're talking about 1 gram spacecraft. So it's only to get there and maybe confirming that, yes, indeed, we're able to travel. For the first time, humanity will be able to travel to a nearby star. And that by itself is amazing. So anything that can be done along these lines would be wonderful. It's showing the feasibility. But solar gravitational lens, you need to travel with spacecraft of roughly about 60 kilograms. 60 to 70 kilograms, because you need to have a telescope, you need to have a communication, you need to have some propulsion, you need to have some energy on board. So our study shows that our engineering study converged on the mass of roughly 60 to 70 kilogram spacecraft on a sail, on a solar sail. So solar sailing is, we just need to tap into the infinite propulsion reservoir that is given by solar radiation pressure. We will use the sun to propel the spacecraft. Because to propel that spacecraft with the lasers, we need to have a much larger area of the sail and much higher power of lasers on the ground. So I think it will be technically possible, but politically challenging, because that type of energy, directed energy, may not be welcomed by spacecraft operators in low Earth orbit, because they will just vaporize the spacecraft. So for that, we'll be using solar sails. And solar sails are good enough for us to reach the focal region of the solar gravitational lens within about 25 years. As technology develops, we can come much closer to the sun. let's say 15 solar radii, and we are now developing solar sails that will be highly reflective, that will allow us to get to that region. And there is two groups of scientists in UCLA and Caltech are developing. One group develops a new generation of solar saline materials, and another group develops a new generation of laser saline materials. So these two groups, essentially led by Professor Arthur Dadavoyan and at UCLA and Professor Harry Atwater at Caltech. So I'm looking at these groups to provide us with materials that will take us to the sun, to very close proximity with the sun, to enable travel into the solar gravitational lens much faster than 7 times the speed of Voyager. Potentially, as the study at UCLA have shown, the sail materials are already have been developed, small pieces of the sail materials that will allow us to travel roughly 20 times the speed of Voyager. So that is something will be very, very important. If we do that, then basically it will be even more attractive. The mission duration will not be as 20, 25 years, will be shorter. But then when we fly a spacecraft to Saturn, the whole mission takes about 20 years. So we're used to that. It's not something that new. But really, developing the project to solar gravitational lens will be very important because it will push every aspect of mission development that we are familiar with. Because, for example, when we fly to Mars, we develop a primary mission would operate, let's say, 90 days on Mars. Like Spirit and Opportunity rovers operated, the primary mission was for 90 days. But ultimately, after 10 years in operation, both of them, Spirit and Opportunity, were still reasonably healthy vehicles. So we know how to build missions that would operate for roughly, let's say, 5 years in mission duration. Now we're talking about 40 years mission duration. We need to make sure that we will be able to implement that technology so that during the 40 years of transit plus science operations, it will be a healthy spacecraft. So it will be multi-generational project, which will involve young scientists and senior scientists to actually develop something like this. And that's exciting by itself. Because as you look at in the history, human history, so we were able to build a large scale structures on this planet. For example, Great Wall of China built it's a multi-generational project. Then pyramids of Egypt. So Egyptian pyramids, very large structures were built by a number of people. But societal organization in those times was not exactly the same as we have now. So now we need to build something similar to the space station. Space station is an international space station was built by number of nations, and it still was launched in 1999, and it's in flight, 25 years in flight. So we have built projects that actually long duration projects. So we need to learn how to do this in the new time and actually enable something the next step towards the solar gravitational lens. So we have a lot of foundation which is solid enough to actually now contemplate, develop, and build that project to the focal region of the SGL.
Okay. So this would be one of many very exciting projects coming about in this decade and the next. Well, and I look forward to seeing them as many as possible being realized because, of course, the more we got and the more overlap there will be with scientific discoveries and so forth. Yes. So earlier I asked about the importance of gravitational research in recent years. And this, of course, has to do with general relativity and how there are questions, unresolved questions, and there have been for decades. But lately, I kind of feel like they've been given a bit of a kick in the rear end because, of course, Webb has come out and it's shown us some observations of the very early universe. And we were kind of hoping they'd say one thing, but they said another, and the whole Hubble tension. So, yeah, can you give us a rundown on that? The state of gravity, if you will. What is it?
That's an exciting period of physics because until probably 1998, we had only one major problem, and that was behavior of spiral galaxies. If you use just
Ooh.
Newton's gravity, you realize that we cannot explain why the arms of the spiral galaxies move much faster than even Newton gravity predicts. it implies that there is a large mass that we just don't see through light. And so essentially it's a hidden mass or dark matter, we call it. So the problem of dark matter exists pretty much in every spiral galaxies. And it was known since 1930s when Fred Zwicky, then professor at Caltech, discovered that indeed spiral galaxies show very anomalous behavior. Then Vera Rubin in the 70s and her group studied those spiral galaxies pretty much everywhere in the universe, observable universe, and they confirmed that indeed the dark matter is a puzzle and phenomenon. We don't know physics. We don't know the mechanism to generate it. There are many different approaches to explain it, but none of them yet sort of brought any sort of feasible explanation. You can think about it's a new particle. Essentially, we have not detected yet, lighter than neutrinos, but highly populated. And you may also think about this maybe a modification of gravity. So it's either two mechanisms are still viable, and we don't know which one will end up explaining this. But in 1998, we realized that we got another puzzle, and that puzzle was reported by the WMAP satellite, showing us that very interesting behavior of supernovae. So supernovae, it's a standard candles when we use those to calibrate distances, and essentially when we apply the distance calibration, we realize that those stars, supernovae, essentially they show that not only universe uniformly expands, as we knew from Hubble's observations. Edwin Hubble, professor at Caltech, shown that universe uniformly expands. Everything is moving away from us. And so after Big Bang, universe expanding very uniformly, moving everything away from every point. But in 1998, we realized that that expansion is not uniform. Something is pushing the universe from within. It's actually expansion is accelerated expansion. Something is pushing. There is a force that pushing it, and we call it dark energy. We call everything that we don't know mechanism for, we call it dark matter, dark energy. But look, dark matter was discovered on the galactic scales. Dark energy was discovered on cosmological scales, on the scale of the whole universe. So now, if I look at the whole energy content in the universe, what we know is only 4% of all the energy in the universe. With the rest of the balance is given by dark matter, which is about 23%, and the rest is dark energy. So here you go. It's the largest crisis in physics, on astrophysics. We don't know what the universe is composed from. We don't know what drives the universe. We don't know what was there before the Big Bang and how the universe evolution went through different stages. And now for star forming phase, galaxy formation, what actually drives the universe? We don't know that. And so we realized that to explain it, some people came up with different models to explain it using different physical particles, different interactions. So we know four standard interactions: gravity, electromagnetic interaction, weak and strong forces. So, but basically they come up with a fifth force or different other forces and different geometric organization trying to explain the behavior of universe. So there are many different explanations, but until even today, we still don't know what actually causing it. There are some plausible mechanisms, and those plausible mechanisms we think we can explore in experiments in the solar system because they provide a mechanism to represent those little anomalies due to new physics in the motion of bodies in the solar system. Recently, we have studied a tetrahedral configuration of spacecraft. And tetrahedral configuration, when you fly four spacecraft on elliptical orbits, and so when you have technology that was developed for LISA, a laser interferometer space antenna, where you have a very ability to precisely measure ranges between the spacecraft using a technique called interferometry. If you do that, you are able to recover very tiny anomalies in the gravitational field in the solar system. And we have shown that this tetrahedral configuration will allow us to reach the sensitivities where we can start probing of these new mechanisms and potentially discovering those predicted anomalies, predicted new forces in the solar system, compensating for all the disturbance forces, for all the known sources of systematic forces. But this tetrahedral configuration holds promise that we will be able to actually detect the presence of the same mechanisms that are driving anomalous galactic behavior, and the same for anomalous behavior of the universe. And potentially in the solar system, if we are flying this configuration of four spacecraft on a highly elliptical orbit around the sun, and within 5 years after launch, we will be able to sort of confirm the presence of those anomalies and potentially discover their mechanisms and study their physics. So that's our response to almost 20 years of research that led to conclusion that we need to have in situ experiments. Astrophysics is wonderful, but those mechanisms are hard to validate, to explore. We potentially, if the same mechanisms work in the solar system, we will be able to explore those physical mechanisms by flying spacecraft in the solar system, conducting something called in situ experiments. That's what we are aiming at, and we are trying to make community aware of this new opportunity to start flying those experiments, potentially flying them in the next decade as well.
Excellent. And yeah, I recently did a write-up and read your study on the tetrahedral formation spacecraft. Yeah. And of course, yes, very interesting. This is going to be a very exciting time. I agree.
In one of your questions, you brought the topic of technosignatures. And
Yes.
technosignatures usually stand for something that we call Dyson sphere. And Dyson sphere is something, the structure that is formed by advanced civilization to source their energy from their host star to drive their technology and sort of access to larger energies. Because essentially, as you can trace the evolution of the human civilization, at the different stages of our evolution, we demand a higher energy. For example, if you look back in, like 19th century, we pretty much energy, we were dependent on the natural resources, the wood, the charcoal, the coal, then oil came, then nuclear power came, then now solar energy is something that is unique. And at some point, we'll be able to harvest energy directly from the sun by putting in space very large solar cells to actually collect power directly from the solar light. And so similarly, advanced civilization may already have built those structures. We call them Dyson sphere because Freeman Dyson was the one who actually, a physicist, who actually came up with this concept, which is interesting.
Hmm.
So potentially imaging of those exoplanets orbiting nearby stars, we can see those exotic structures if they exist around nearby stars. But also an interesting topic is that if there is advanced civilization and not that much advanced compared to us, maybe by maybe a couple hundred years more advanced than us, we'll be able to fly a laser transmitter to the focal region of their host star and transmit a signal through their host star gravitational field towards us. And in our recent study, we just have shown that with the constellation of telescopes on Earth, or maybe in the Earth vicinity, we will be able to already detect the presence of the signals that would be sent to us. So that is quite interesting. That with moderate laser power, let's say 1 kilowatt only, we can actually cover interstellar distances and provide a very significant signal to adjacent nearby stellar systems. So we are not able to transmit those signals yet, because for us to be able to transmit, we need to travel to the focal region of the solar gravitational lens. But if they are able to travel to the focal region of their lens, they will be able to send us that signal. And with the telescopes on Earth or in space, we will be able to detect those signals now. And essentially, we come up with the third strategies, how actually you can look for those signals. That would be an interesting exercise, interesting study, because Optical SETI, Frank Drake and Jill Tarter, they started SETI search for extraterrestrial intelligence back in 1960s, and so that project was had a very exciting time. And now it's funded by again Breakthrough. They're doing Optical SETI, looking for light emission or laser emission from different sources, but not gravitationally amplified. With our study, we have shown that if there is a desire to send us a signal, then that advanced civilization can actually build that laser, and not that much advanced. We have those technologies already. You can go and buy 1 kilowatt laser, essentially 100 kilowatt lasers are available. You need to space qualify and fly them. So, but with the technology that we already have, potentially, we can fly that and we can transmit ourselves. But let's not wait for our readiness. We can detect those signals if they already sent to us. So that is interesting. It's opening up another era, another area of research, potentially looking for the transmitted signals. That will be exciting sort of revelation if we detect signal like that. That will be an interesting revelation that, we are not alone. And before we will be able to travel to the focal region of the SGO, will not only we will be able to image that exoplanet which we're interested in, but also collect and maybe communicate with that transmitter that actually sent us the light. So that will be another interesting step for us to consider. So, but for that, we have already the telescopes, we have already the constellation of spacecraft with the capabilities that will allow us to detect those signals. It's just the time to begin. So we have everything in place.
Yeah, and I remember reviewing that too and thinking, wow, interesting. In fact, we discussed transmission of communication signals energy through solar gravitational lenses, and oh yes, quite the interesting, fascinating concept there.
And
Well, as a personal aside, I'd say finding evidence of extraterrestrial intelligence would be the greatest and scariest thing we ever did. But I hope that we do someday.
Exactly. Look, in my research, I was just looking at physical mechanisms to see if
Mhm.
physics prohibits it. I was not motivated to do anything. I was just putting assumption. What if? What if there is a transmitter and it's able to transmit in monochromatic light in one wavelength like lasers do? And so putting it in sort of reasonably motivated orbit and transmitter configuration, what can that transmission allow? And to my surprise, that indeed we can have very good signal to noise ratio because we can actually see that signal on the background of the host star and all the other noise sources that we will optical noise that we will be able to remove. And so essentially that was my revelation that physically and technologically it is possible. Now we can think, if it is possible, are there anybody transmitting towards us? What would it take to detect those signals? And essentially, this work that we have published recently, helping maybe open a new area for optical within optical city research. Maybe the community will be able to look at it and so see if those signals may be also searched for. So that was interesting revelation. But you're right. If we'll get a confirmation that we are not alone, how will that change us? How long will it take to percolate that idea among the inhabitants of this planet? We now, what, 8 billion of people, right? So, and you and I, we're having this conversation on Tuesday afternoon. It's wonderful. And majority of people may not have the luxury of thinking about this, right? So, because we have education, we have sort of life that allow us to think about those questions. Many people cannot make ends meet, right? So they have to provide for their life. So that idea that we are not alone will not sink among everybody on this exoplanet in the same on this planet at the same time. So basically, 8 billion people, probably majority of them don't really care. Not they will be interested, but they will not realize how important that is for the civilization. How will it affect us? So that's the set of questions, our lifestyle, our sort of traditions, all built with understanding that life is finite, and so we alone we have to rely on ourselves. How will that change? How will that actually motivate to change the way we live and treat each other on this planet? How that will motivate to save environment on our planet? That's something I think I see a very positive impact of that discovery. So that will help us to, you know, to develop life on this planet, to cherish life, and actually, treat each other in a better way, so that we'll recognize that look, life is something that was given to us. We need to keep it, and so that will be very
Yes.
interesting. Keep an environment and life, right?
Yes. Well, yeah, and I absolutely hope you're right, and that this is it proves to be a gift that helps us find our footing and do better because yeah, the neighbors could be dropping by. We need to clean this place up, right?
Exactly.
So, yes, and tell your brother and your sister to stop fighting. Well, well, yes, I share your hopes for that there, and I want to wish you the best of luck because many times when I have guests on the show, I have to admit that your proposal is not only is it really interesting, I want to see it succeed. I want to
Oh,
see what this can do. I'm excited for that. And yeah, well,
look,
hopefully you can convince others of that too.
Matt, look, I'm a man on a mission. By the time I'm reaching, so to reach this, to fly the mission and reach the focal region of the solar gravitational lens takes time. And so basically, it takes about what 25 years to get there. We launch in about what 15 years from now. So by the time I'm 100 years old, I want to be able to see the surface of exoplanet. So I'm a man on a mission. I want to keep popping up on your show until then. And then when I see the exoplanet, then I think I'll go. But before that, you will see me often on your show reporting on the progress of what we are doing these days.
Excellent. I'm going to hold you to that too. Okay.
Excellent. All right. Very good.
Definitely, yes. I mean, yeah, updates are much appreciated and breakthroughs even more so. Oh, can you imagine? All right. Well, thank you for coming on. And yes, I hope to have you back on again. And I hope there's some exciting news or just exciting new ideas and
Excellent.
concepts you're working with. Okay.
Excellent. Thank you very much. Thank you for having me.
Thank you. No problem. Thank you.